Just please response because I cannot right now see the message whether it is full screen. Just for a second, just unmute yourself and whether it is visible full screen or not. Just yes or no. Okay, so good evening to all of you. So myself Samaris Ghosh. So today we will discuss about we are discussing about characterization of polymers, elastomers, and composite, already taught by Professor Santanu Chattopadhyay. And here I am Samaris Ghosh as a research scholar to do my TA work, taking this doubt clearing class. So we have till now discussed different spectroscopical technique, and last week, due to some unwanted reason, I have not taken that class and rescheduled that class today, same time. So uh, we are discussing about NMR. So we have discussed 10 NMR, 13 CNMR, and we have also introduced solid state NMR little bit. And today we'll start from solid state NMR, then we'll discuss different thermal characterizations technique. So we have already discussed different coupling and also to minimize different coupling, how we should uh, do different technique to get a uh, clear peak from solid state, because there is a chance of different interaction due to material used here as a solid state. And we have also discussed different effect, cross polarization to get remedy and to get the a very clear peak. So this is basically a schematic diagram of a solid state instrument. And what are the different component? So first one is the sample holder. So you need a sample holder to put the sample, and that has also different size. For example, it is 7.5 centimeter long and 0.3 centimeter diameter. Obviously, you need a magnet to generate the magnetic field, external magnetic field, and electromagnet or permanent magnet can be used operating from up to 100 megahertz. There is the strength of that magnetic field. That much amount it can generate. And sometimes superconducting magnet also used, and that operate at higher strength with 230 megahertz. And the strength and the direction of the magnetic field, that will not change from a different point. And also there is one sweep generator, that is variation in the strength of the magnetic field. Just by modulating that, you can modulate the magnetic field. Obviously, you need a radio frequency, as we know that for NMR to make the resonance, we need radio frequency receiver. When the radio frequency is passed through the sample, some absorption will take place, and based on the absorption, we will get the signal. And there is also another important thing, there is the detector that will actually separate it out different signal from each other, and those are the radio frequency, bridge method, and nuclear induction method, by which we will get separated signal. Here this is the sample uh, holder. So you need powder sample packed in a specific dimension tube, ceramic tube or ceramic rotor for mass experiment. What is mass? Mass is the magic angle spin. The rotor basically are cylindrical type, and it has different diameter from 7, 4, 3.2, 2.5, 1.3, and 0.7 millimeter, which can accommodate between 500 mg and 1 mg. So you may put sample at a higher amount. For example, in case of if it is the diameter is 7 mm, you may put say 500 mg, or if the diameter is very small, 0.7 mm, you should keep the sample 1 mg, and actually it will rotate or to do the mass experiment. And that sample must be finely grounded so that efficient packing can take place. And the bottom of the rotor with a black silver permanent marker, it is required because to check the speed of the spinning there is a tachometer, so that's why you need a black permanent silver marker. Now how it looks like the solid state dynamo peak. So this is the example of a ethyl vinyl acetate copolymer. So we know that EVA, it can be plastic, it can be rubber based on the uh, component or concentration of phenyl monomer that is used to synthesize that copolymer. So based on the VA content, it may behave as a rubber, also it may behave as a steel. Now the importance of solid state NMR is how it can differentiate uh, by varying the VA amount. So you see there is a peak at 169 and also there is one peak at 70. So that is because of the carbonyl group and CH group. So carbonyl appeared at 169 ppm, CH appeared at 70 ppm, and methionine group that appeared at 20. This is the CH3 of the phenyl, and 40. This is in that region. So two overlapping peaks is around 32 and 33. So 32.4 and 33.4. So the crystallinity of the AVA actually varied. It may have orthorhombic type crystal or it may have the monoclinic type crystal. Now for those two different crystal, you will get different peak from the solid state NMR. So first one at 32.4, this one is because of the orthorhombic, and the next one at higher ppm, that is 33.4, that is due to the monoclinic type of crystalline morphology. Now here it is more prominent that how if I increase the VA content, the NMR peaks will different. For example, the peak with, so this one is the point, if phenol content is 0.5, then phenol content is 12, then 18, then 28, and then 40. So I am continuously increasing the VA content. So with increment of the VA content, you see the peak around 31, it is continuously increasing, and that line actually indicates that monoclinic crystalline nature or monoclinic crystalline signals is increasing due to the increment of the vinyl content. So what are other different applications of solid state NMR? So to check the phase distribution, morphology, and spin diffusion of different polymers, we can go for the solid state NMR study, and also characterization of molecular structure, dynamics of in solid polymer, and also hybrid electrolytes. We can do the NMR study to determine the different protein structure. It is very important to go for the solid state NMR, and also since the solubility of conducting polymer is very poor in any organic solvent, it is required to do the solid state NMR to know the structural behavior or the molecular structure of conducting polymer. And also for composite with different loading of filler and another nanoparticles, functionalization of different elastomeric material to probe different interaction, we will go for the solid state NMR. So these are the different application area where solid state NMR is very important, and it may be that proton NMR is not possible to different insoluble polymeric material. So that was up to solid state NMR. So mainly we will focus today about different thermal characterization of polymeric materials. So thermal analysis basically is a branch of material science where the properties of materials are studied by scanning the temperature or by changing the temperature. There are different methods are used to distinguish from different analytical technique, and also different property we will measure through different thermal analysis. So first one is the differential scanning calorimetry. So this is very much popular in polymer industry R&D. DSC actually measures that how much heat is absorbed or heat released during the various transition in the sample due to temperature scanning. And differential, why it is differential? Because we are measuring the difference as compared to a reference sample. So there are two different holder. One is sample holder, another one is reference holder. I will discuss in the next step. And why it is scanning? Because we are ramping the temperature from lower to higher or higher to lower. And why it is calorimetry? Because we are measuring the heat. So these three terms actually indicates what we are going to perform or what we are going to study from DSC. So differential means the difference in between the sample and reference. Scanning means what is we are scanning, it is the temperature, and calorimetry means we are measuring the heat. So basically what we are doing, we are scanning temperature and measuring the heat difference between the sample and reference. And DSC measurement are both qualitative and quantitative, and it provides so many information about physical and chemical changes involving during the temperature ramp. So in case of endothermic process, sample will absorb energy, and in case of exothermic process, obviously sample will release energy, and based on that energy absorbance or release, the heat will differ. This is the principle. So DSC is a thermoanalytical technique in which the difference in the amount of heat required to increase the temperature of a sample and reference is measured as a function of temperature, what I have already discussed. The difference in heat flow occur due to the occurrence of two major events. The first one is the heat capacity of the sample, which increases with temperature, and the different transition happened during the increase of the temperature, and that event superimposed on the heat capacity baseline. So this is the schematic diagram of a DSC. So these are the two sample two holders. So this one is the sample holder, this one is the reference, or this is reference, this is sample. There is also chromel disk, that is actually the thermo calorie to measure the heat or temperature, and also there is a aluminum wire that is also attached with both sample and reference, and a thermoelectric disk or that is made of constantan to probe the temperature. So this is the uh, schematic also of a DSC instrument. So this is sample, this is empty, and or it is a reference, and we are measuring the difference in temperature or heat flow. So here again we will discuss the working principle in a more deeper way. So this is the sample, this is the reference. The first one is the heater that is providing heat to the sample. There is another independent heater that is providing the heat to the reference, and this is basically a amplifier that is also required to uh, to measure the heat difference. And you may scan the temperature in a linear fashion. So you are increasing the temperature at a specific uh, rate, it may be 5 degree or 10 degree or 20 degree, and with the increment of temperature depending on different physical phenomena occurring in the sample, we will get different transition. So this is showing the actual DSC thermogram. So what we are plotting here, we are plotting heat flux versus temperature, and in upper direction is the endothermic process. Obviously, in the opposite direction, this is the showing exothermic process. So first, a transient starting, that is basically due to the heat capacity. We will discuss how we can measure it. And after that, there is a second transition, that is called the glass transition, and obviously it is an endothermic process. So it absorbs the heat when a rubbery material or a glassy material is, with the increment of temperature, transition to the rubbery type of material, from glassy to rubbery. So obviously it is an endothermic process, so it is absorbing the heat, and you are getting a transition type of, or a increment of the peak. The third one is the crystallization peak. So since crystallization is exothermic process, so when a material is crystallizing, it is releasing heat, you will get a exothermic uh, process, and the peak will go in a exothermic direction. And the after crystallization, when the crystals melts, so obviously to melt the crystal from a agglomerated or from a more arranged state to a unarranged state, it will require the heat to melt the crystalline particle, and it is a endothermic process. That's why you are getting this peak, and at the end you are getting a ending transient. Now if you look at the mathematically, so what we are actually measuring, or how, on which principle DSC is working. So this is the DHDT, that is the heat flow. Now how much heat is flowing under unit time, that is equals to Cp, that is the heat capacity, into dT by dt, that is temperature rate or heating rate, plus function of T and T. So this T is the absolute temperature and this T is the time. So based on this principle, actually DSC is working. So this is the typical DSC curve. So from the DSC, you will know the different physical changes, what is happening when you are increasing the temperature, and based on the area under this curve, you can calculate that how much energy is required. That is also possible from DSC. That's why it is also a quantitative uh, analytical technique. Now, so this is also showing the same different transition that is happened during the heating of a material. Different thermal transitions are possible. First is the glass transition, that is endothermic process. The second one is the crystallization transition, that is exothermic process. And then melting transition, that is endothermic. And finally, when the bonds degrade, so it's not that it has to be exothermic, it may be also sometimes endothermic. Now the melting, that is basically first order transition. Why it is first order transition? Because the Gibbs energy actually changes during the melting. So the melting point is at which temperature that crystalline phase of polymers become more disordered and form a viscous liquid phase. Now polymer consists of very long carbon chains, and also they are held together by strong covalent bond than the small molecule. Due to that, they have stronger intermolecular interaction than the small simple molecules. Now, only crystalline material and semi-crystalline polymers show melting transition. So obviously, since polymers are very has very entangled structure, and it is not perfectly crystalline, so it is difficult to get a very sharp peak in DSC for a polymeric type of material. But there are some polymers, those are semi-crystalline type polymers, and it will show in melting transition. So you will get a peak that is corresponding to the melting of that crystalline zone. But amorphous polymers do not show any melting condition, and you will not get any peak like a so you will not get any TM or TC from the DFC in case of amorphous type of polymer. And it is a phase transition, so it is uh, the transition happens from solid to liquid when it is melting. And why it is first order? Because you know that the melting is actually del G del T, the change in Gibbs energy. That's why this is a first order transition. You see, from this to this, the phases changes after this transition. Now, our main interest is the glass transition, because as you know, the glass transition is the property of a amorphous type of material or semi-crystalline solid. So in case of semi-crystalline, you will get both TC and PG, that is crystalline temperature, or TM melting temperature, and PG glass transition temperature. Now the crystalline portion remains crystalline during the glass transition. Below glass transition temperature, the amorphous regions of a polymer are in the glassy state, and in this state the molecules are basically frozen. On trace as the segmental movement of the polymer chain, those are freezed, and there is no segmental motion below the glass transition temperature. But it is not a phase transition. So as in case of melting, the solid is converting to liquid, but in case of glass transition, there is no phase change is occurring. And why it is secondary transition? Because the property like thermal compressibility, isothermal compressibility, or expansion actually changes during the glass transition. So since it is already a we know that thermal expansion is referred to like 1 by V into del V del T at constant pressure, and thermal compressibility is equal to minus 1 by V del V del P at constant T. So these are already a derivative of volume. So since the further changes actually occurring, that's why it is second order transition. Now, what are the different thermocouples are used in DSC? So there are various kind of thermocouples are available. For example, the copper constant 10. So for that, there are limitations, that is up to 250 degrees centigrade you can measure or you can study. Maximum temperature limit is 250 if you use the thermocouple copper constant. If it is iron constant, then it is 450 degrees centigrade. For chromal constant, you may reach up to 1000 degrees centigrade. For chromal aluminum, it is 1350, and the platinum with 10% rhodium, you can reach up to 1600 degrees centigrade. And for tungsten and ruthenium type of thermocouple, one can go up to 2400 degrees centigrade. So depending on different thermocouple, obviously you can cover a wide range of temperature during the DSC study. Now there are different types of DSC based on the mechanism how it works. So first is the heat flux, and in heat flux there is also disk type measuring system. There are others type of measuring cylindrical type measuring system. These are not so much common. The next is the power compensation. We will discuss what is heat flux DSC and power compensation DSC. So these two DSC are the mainly used in any lab or any R&D. The third one is the modulated DSC, hyper DSC, and pressure DSC. So these are the 5 different types of DSC, but most common is heat flux and power compensated DSC. Now, what is heat flux? So basically in heat flux, we are measuring the heat difference. We are measuring the different flow of heat when the temperature is changed. So in a heat flux mixing, a pan containing the sample and an empty reference pan are placed on a thermoelectric disk enclosed by a furnace. There is a single heat sink that is the furnace. So from that heat sink, heat is provided to both the sample and the uh, reference empty pan. Now as the furnace is heated at a linear heating rate, for example 10 degrees centigrade per minute, the heat is transmitted to both the sample and reference through the thermoelectric disk. Now the physical changes occurring in the sample, due to that physical changes, there will be the difference in the temperature. Now we are measuring or we are monitoring the temperature both the sample and reference. Now to keep the temperature same, there will be difference heat flow from the heat sink to the sample and reference, and that is actually plotted with respect to temperature. So the difference in temperature of the sample and reference pan due to the heat capacity of the sample is measured by area of the thermocouples. The resultant heat flow actually calculated by the thermal equivalent. That is the main principle or Ohm's law. Q equal to R into del T. Then Q is the sample heat flow, del T is the temperature difference between the sample and reference pan, and R is the resistance of the thermoelectric disk. Now a DSC consists of different elements. So first of all, a cell, that is the heart of a DSC, is there. The cell is connected with a gas inlet through which different gases pass. So you may study DSC in inert atmosphere or in open atmosphere or in oxidative atmosphere by purging different gases. What is your requirement? Based on that, you can do the study in different environment. And based on this session, there are two primary types: is heat flux and power compensation. So already I have told you that in heat flux there is a single heat sink, that is the single furnace, that act as an infinite heat sink to provide or absorb heat from the sample. Now the advantage of heat flux DSC is generally it includes the better baseline, better sensitivity, and sample atmosphere interaction. The key components are the sample pan, typically an aluminum pan, and a lead, which is combined with the reference pan, always the same material as the sample pan. Obviously, if they are different, so based on the different heat capacity of different material, we cannot get the accurate data. The dynamic sample chamber is the environment of the sample, pan compartment, and the particle. So nitrogen is the most common gas, but other inert gases like argon or helium also used. When using an oxidative atmosphere, either air or oxygen are required to purge. The heat flux DSC is based on the change in the temperature between the sample and reference. Now, what is power compensation? So, in heat flux, we are measuring the heat difference, and we are monitoring the temperature, and based on that, heat are absorbed or is released from a single heat sink. Now, in case of power compensation, a small individual furnace use different amount of power to maintain constant delta T between sample and reference. The advantage here include faster heating and cooling and better regulation. Now, this type of cell is two individually heated with platinum heater monitor the difference between the sample and reference. So here for sample you have a independent heat source, for reference you have another independent heat source. So that's why we can uh, very do the test at a very fast rate, and we can also increase the we can achieve a faster heating or cooling and better resolution, since two independent heat sinks are used for sample and for reference. And platinum resistance thermometers track the temperature variation for the sample and reference. So holes in the compartment leads allow the particles to enter the contact the sample and reference. So based on your requirement, whether it is inert atmosphere or oxidative atmosphere, you need to purge different gases. There are physical differences between the heat flux and power compensated thermal analysis. The resulting fusion and crystallization temperature are the same. The heat of transition is comparable quantitatively. So this is basically a schematic diagram of a power compensated DSC. So here this is sample fan and it is a independent heat source. So this rectangular shape is actually an independent heat source. This one is the reference fan and this is an independent heat source for the reference. So sensors that is used here is a platinum resistance thermocouples, separate sensors and heaters for the sample and reference, and furnace that separates the blocks for sample and reference. For temperature controller, differential thermal power is supplied to the heater to maintain the temperature of the sample and reference at the pre-programmed value. So what is the difference between the heat flux and power compensated DSC? In heat flux, sample and reference are kept in a single furnace, but in case of power compensated, they are kept at an individual or separate furnace. In case of heat flux, heat flow to the sample and reference is measured. In case of power compensated, the amount of power required to maintain the same temperature difference is measured. The temperature difference is converted to heat flow using the mechanical calculation. That's why it is heat flux. And in case of power compensated, the heat flow is measured directly as the amount of power required, that is directly proportional to the heat flow. Now there are different sample preparation. Actually, you can go for 3 to 20 mg. There is small amount of sample is required to do the DSC test. So usually 3 to 5 mg sample is taken, and there is a small sample pans. So these are the different sample pans of different made by different inert metals like platinum, stainless steel, or aluminum. There are different configuration of pans are available. For example, open, pinhole, or hermetically sealed pans. Those are sealed very tightly. Same material and configuration should be used for the both sample and the reference. Otherwise, you cannot uh, get the accurate data. And the material should completely cover the bottom of the pan. So the bottom surface, it should be covered totally by your material. If it is not covered, so obviously there will be not homogeneous heating of the sample. For the thermocouple will read or will check different temperature at if it is connected at a specific point at the bottom of the sample holder, and if there is no sample, so obviously it cannot get the what is the changes happening during the changes happening physical changes. It cannot measure the temperature, and you should not take a very high amount so that it can flow from the sample holder. And it is important to do the test under a low heating rate. So if someone is doing the test at a 5 degrees centigrade per minute and the same material is tested at 20 degrees centigrade per minute, there will be a slight difference in the data. Now, what are the experimental conditions you have to set prior the testing? So first, you should set the temperature range. So from uh, the lower temperature to higher temperature. So first you set the lower temperature. For example, in case of rubbery material, or to know the TG, you should set the temperature minus 70 or minus 50, minus 16, like that. And you may go for 300 degree, 400 degree, or above 400 degrees centigrade based on the material types and reference pan, and also the heating rate, whether if we will go for from lower to higher at a 10 degrees centigrade per minute, it should be predetermined. Now, what is the effect of heating rate? Now, heating the sample at low heating rates actually increase the resolution by providing more time at any temperature, And transitions due to the kinetic process such as crystallization are shifted to lower temperature at highest cooling rate or higher temperature at high heating rate. So what actually happens if crystallization or your material has some semi-crystalline type material or crystalline nature, if you do the DSC at a lower temperature rate, so you will get the TC value at slightly lower temperature. For example, if you are scanning at a 5 degree centigrade per minute and you are getting TC at 60 degree centigrade, and if you do the same testing at 20 degree centigrade per minute, you will get TC maybe uh, 65 or 67, like that. So there will be slight changes. If you use multiple heating rates, then start with 1 degree and up to 10 degrees centigrade per minute. Melting is a thermodynamic phenomena. The onset of melting does not change significantly with heating. Evaporation, dissolution, and decomposition are kinetic process, so those will be affected with the heating rate. So basically, the kinetic phenomena actually uh, they will shift based with different heating rate. But those properties, those are thermodynamic phenomena, it will not change significantly. So here it is showing that with increment of heating rate, so from 2 degree to 20 degree centigrade per minute, how the melting temperature of indium actually changes. Since it is a kinetic phenomena, so there is a slight change in the uh, melting temperature. So when it is 20 degree centigrade per minute, it will get around once 57, like that. Yeah. So before sample study, we first calibrate the DSC instrument. How one can calibrate it? So calibration of DSC done using the indium metal, since it has a very specific melting point. So calibration of an instrument with a metal when polymers are to be studied appear to be not appropriate. To overcome this, an effort has been made to calibrate DSC with the polymer. So the true melting temperature of indium is 156.7 and the observed calibration is 157.4. So it is 0.7 degree high and the instrument values must be adjusted down to accommodate the true melting temperature. Now what are DSC actually determine? So it can measure the TG, or you will get the TG value of any polymer, temperature at which amorphous polymer or amorphous part of a crystalline polymer go from hard glassy state or brittle state to soft rubber state. The melting point Tm you can get from the DSC, so at which the crystallinity or crystalline zone melts. You will get delta Hm, that is the heat uh, required or absorbed during the melting by calculating the area under that curve. The crystallization point Tc at which the crystallization occurred, you will get that also from the DSC, and vice versa. And obviously the accordingly the heat the released during the crystallization you can calculate from the area under that curve peak. So from DSC we can get a the TG of any unknown sample also, and we can measure different physical properties of any material. Second important thermoanalytical technique is the thermogravimetry. So it is a technique in which the change in the weight of a substance is recorded as a function of temperature or time, either as a function of temperature or as a function of time. The instrument used for thermogravimetry is the thermobalance, and data recorded in form of curve known as the thermogram. Now, TGA measures the amount and the rate of weight changes of a material with respect to temperature or time in a controlled environment. Hmm. A TJ consists of three major parts: a furnace, a microgram balance, an autosampler, and a thermocouple. So these are the major parts of a TJ instrument. Now the furnace can raise the temperature as much as high 1000 degrees centigrade, which is made of quartz. The autosampler helps to load the samples onto the microbalance, because here also you need a very small amount of sample. The thermocouple sits right above the sample, so it will measure the uh, heat of the sample, and care should be taken at all time that the thermocouple is not in touch with the sample, which is in a platinum pan. So it should not touch the sample. It may react at that high temperature with the material. That's why it should not touch. Now, what are the different application area of TGA? So first of all, to know the thermal stability of the material, you should go for TGA. Different composition, to know the composition of a multi-component or a composite material, you should go for the TGA. The third important uh, application is to investigate the oxidation or oxidative stability of the material, and obviously the most important is the estimated lifetime of a product. And also from TJ you can get the information about decomposition kinetics, the effect of reactive or corrosive atmosphere on the material, moisture and volatile content of a polymeric material. So these are the different uh, area where you should go for the TGA analysis. Now, what are the TGA thermometric capabilities? So composition analysis, decomposition temperature, and also you can check the rate of degradation, the estimated lifetime of its surface life by doing the TGA at a faster rate, heating rate, oxidative stability, evaluation of polymer flammabilities, and also thermal stability. Now, the temperature calibration in the TGA can be done by two ways. So, the method of making use of the melting point of a pure metal and the method of utilizing the Curie point temperature, these are the two basic calibration techniques by which the TGA can be calibrated. So, in case of the melting point, one of the metals processed in a ribbon shape and is suspended on the TGA suspension wire, and the weight of about 100 mg is attached at its tip. Now, when the metal is melted or fused by heating, the weight drops, and the weight drops since there is a microbalance, it will measure the weight. You will get the weight loss from the TGA or thermogram. In the latter method, the standard substance verified by the International Congress on Thermal Analysis is measured. The standard substance are actually ferromagnets. So from here, by being different Curie temperature, you can calibrate it. So it is intended to calibrate by measuring the apparent weight change when the appear in steps at Curie temperature by making use of permanent magnet. So ferro to permanent magnet, Curie temperature at where the mass will change, and you are measuring that mass change. So this is a typical thermogram where the plot is loss of weight versus temperature, or it may be time also. And this is the onset of the degradation or weight loss. This is the midpoint, and here it is the end set of the weight loss. Now here it is also important to uh, highlight the effect of heating rate. So since this is the kinetic phenomena, the mass loss during the different reaction or different degradation with the heating rate, that the onset for the temperature at which actually the mass loss takes place, that will change. So with higher the heating rate, the temperature corresponding to different mixtures will be shifted towards the higher temperature. Now, how one can determine different composition of a composite diamond material or a filled rubber material? So first of all, this is the TGA under inert atmosphere. Nitrogen is used. Now, these weight loss. So first, this is the two-step degradation. This green color line, it is showing there is a two-step degradation of the material. The first degradation started around 40 degrees centigrade and it ends around 50 degree or 47 degrees centigrade. The total weight loss is 71.6%, 46%. Now when the atmosphere change from nitrogen or inert to oxidative atmosphere or air, the second loss takes place, that is around 28.56%. Now what is the role of the nitrogen or oxygen? Now since in oxygen there is oxygen, so there is a chance of oxidation when you are increasing the temperature. So based on the different uh, nature of material, it has different tendency to oxidation. In that way, the obviously after oxidation, the mass will change and we will get different uh, data from the TGA at different atmosphere. So here it is showing, see, around after 400 degrees centigrade, when it is nitrogen, his degradation this takes place at higher temperature, but if it is oxygen, the degradation starts at slightly lower temperature. Since in presence of oxygen or other oxidizing agent, the oxidation will be enhanced and it will deteriorate the material fast. So this is the importance of TGA and DSC. So from TGA we can check the thermal stability, we can check uh, different composition, we can also check uh, different oxidative or the material behavior in presence of oxygen or nitrogen, how much it is prone to oxidation. We can also check from TGA, and also we can assess the surface life of any product from the TGA. These are the few questions. The first one is the significance of second heating scan in DSC. Actually, it is better to do the DSC or to take the DSC data from the third cycle. So what is the third cycle? First, you preheat the sample from the starting temperature to end temperature, then again cool it from the final temperature to the starting temperature. So this is the two cycle. After that, when you are heating it from the beginning, you will get that cycle data. Now, why it is important? So the options are to determine the glass tension temperature, erasing the thermal history, two properties of the material. So actually this for all of the above, to get the best data, we need to take the third cycle data. So answer is the all of the above. Otherwise, what happened? It may be there are some impurities that is not behavior of your actual material. You can also get that data. So that's why first heat it, cool it, and then the third heating you get the data. Which one of the following material is used to calibrate the DSC? So we have discussed that we can calibrate DSC by uh, metal which has a very specific melting point. So the option answer is the in India. It is required to calibrate the DSC. Now, which of the following statement is correct? The options are the in heat flux DSC, heat flow is measured directly as the amount of power required which is directly proportional to the heat flow. In heat flux DSC, the temperature difference is converted to heat flow using a mechanical calculation. In heat flux DSC, the amount of power required to maintain the same temperature is measured. And last is the major advantage of heat flux DSC is its ability to resolve overlapping conditions that occur in any polymer. So the answer is the B. In heat flux, the temperature difference actually converted to a heat flow using the mechanical calculation. So thank you. If you have any doubts, you can ask me. Otherwise, I'll stop here. And again, we'll meet tomorrow.